Let's get started. So today we're finishing up chapter 17. And I'll probably make the chapter 17 homework due probably a week from Sunday because it's spring break, so I'll let it be due the weekend after spring break. So anyway, we're finishing up by talking about atoms, particularly ways to make atoms. And so from what we talked about in our nucleophilic acyl substitution thus far, we know one way we can make amides is from acid chlorides plus amine, which will give us our amide plus HCl. We can take an anhydride plus an amine, and that will give us our amide plus our acetate, ammonium acetate as our byproduct. And you can take an ester and throw in an amine and make an amide. So from our nucleophilic acyl substitution, we know we can make amides from acid chlorides, anhydrides, and esters. And the equilibrium in each of these cases is going to favor the amide because of the pKa difference between the nucleophile and the electrophile. So review classic stuff that we've talked about a lot. In reality, in 2015, if you want to make an amide, the only way people might actually use consistently is an acid chloride plus an amine to give an amide. Practically speaking, that's probably the way you would make an amide with the chemistry I told you before. So the most useful one. Hello? I thought you said you weren't going to take this one. I was going to talk about how proteins might make proteins. Now I'm a little bit nervous with a card-carrying biophysicist and biochemist in the room. By the way, Professor Huxford is teaching Biochem 560 this summer. So if you're interested in biochemistry and you want to take it soon, or if you don't like biochemistry and you want to get it done within 8 weeks over the summer, you should take Biochemistry 560 with Professor Huxford. I think that's why he was here. Really? Okay. Well, you wanted this nice, great lecture. So, moving on. So, amides. How would we really make an amide in 2015? So, the ideal way to make an amide, particularly in the context of making a protein or making a peptide, which is just a smaller version of a protein, would be starting out with carboxylic acid and adding an amine. This would be the ideal way because carboxylic acids are stable. You can buy them pretty much anywhere. If you want to make a peptide, you'd make it from the amino acid. And amino acids are cheap, rarely available. You can actually probably buy any amino acid from Whole Foods or GNC if you wanted to, although I don't know if I would trust the purity or what's actually in it. There's been studies that say supplements which are not regulated by the FDA aren't really what they say they are, or if anything, they're making trace amounts. Scientific analytical chemistry studies have shown this, but that being said, if you trusted it, you could technically buy amino acids from GNC for really cheap. So carboxylic acids and amino acids are really cheap, they're really readily available. Thus, if you want to make an amide, the perfect way, most economical way, perhaps the most straightforward way, would be to take a carboxylic acid, take a secondary amine, and have the amide form. Why won't this work? If you take a carboxylic acid and an amine and stir them together, what will we get out? What would the product be of taking a carboxylic acid and amines, which are known to be basic? What would we get out? Yeah, we'd have an acid-base reaction. This would not add into the carbonyl. What we would do instead with the amine reduct as a base, deprotonate. Giving us our carboxylate plus our ammonium. So unfortunately, we can't do this, albeit that would be the best way. What nature makes happens. So in protein synthesis, who has taken biochemistry so far? How many have taken 560? The majority probably take 360, I think. Has anyone had Professor Hexford? Well, the students who are thinking about taking 560 over summer, Professor Hexford is awesome. An awesome biochemistry teacher who really cares about the big picture. So, how does biology make a protein? How do they make an amide bond? Because every one of us are making millions of amide bonds as we speak. No, they catalyze it. But what does biology start with? Carboxylic acids, right? Because we eat a protein. Our body breaks it down into the basic amino acids and then builds it up into another protein. So nature makes some carboxylic acids. How does nature do it? With an enzyme, they do. But enzymes still aren't good enough to make amines out of carboxylic acids, to make amides out of carboxylic acids and amines, because you can't overcome the acid-base chemistry. You just can't. So what do? Chemists, at least from what you guys know, chemists take a carboxylic acid and they make an acid chloride, because you make acid chloride from carboxylic acids. And then they throw in amines. So in this case, you could argue in the first step, we're making a more reactive acid chloride, and then the amine acts. And of course, with the acid chloride, you don't have to worry about this acid-base step. So in this case, what you could say is from a carboxylic acid, you make the acid chloride using thionyl chloride. And you can imagine this as activating the carboxylic acid for the OH to become a good leaving group. So activation of carboxylic acid. And indeed, that's what nature does. Nature takes ATP and an enzyme, so A for adenine, but I'm going to draw the TP part out. So here's a triphosphate part of ATP. Nature takes an enzyme plus ATP and gets out a phosphate ester. So the enzyme will activate the carboxylic acid in nature to give us a phosphoester. And so let's ask now, how will we change the equilibrium? What's the pKa of what? Or OH conjugate acid? About 16. What's the pKa of phosphoric acid? I guess in this case, what's the second pKa of phosphoric acid? About 7, right? So by going from here to here, nature is doing two things. One, it's lowering the pKa of the leaving group from 16 of its conjugate acid to now about 7 of its conjugate acid. So this is more closer to an acetic anhydride, to an acid anhydride now, than it is to a carboxylic acid. So it's making it a better leaving group. And then the second thing it's doing is it's removing the acidic proton. So now when an amine sees this, it's not going to have a proton to pluck off to give the ammonia. So two things are happening in biology that allow amides to form so fastly: activation and removal of the possibility of acid-base chemistry. And so then the final part of a biological amine formation is the amine coming up and just doing a typical nucleophilic acyl substitution, kicking off adenosine monophosphate, so AMP for those who like molecular and cellular biology. So that's how we make amides in our body. So we make it through a nucleophilic acyl substitution like we've been talking about. However, we take the carboxylic acid and we activate it to be a better leaving group. So in situ, it makes something that's very similar to an anhydride, and then chemistry happens. Typical nucleophilic acyl substitution to make an amide mechanism. So there's a proton transfer I didn't draw. I don't think I should have to draw the proton transfer at this point. But there is a proton transfer I didn't draw to give us the product. What was your question, Bill?
Does that make it cyclic?
What do you mean?
So
it's kicking this off here.
Yeah. So is the AMP cyclic AMP or is it regular AMP?
I think it's just regular AMP. Wasn't expecting someone to bring up chem ever in the second semester organic chemistry class. That's just AMP. I don't know enough about the chemistry of, I don't know, obviously AMP's got to turn into cyclic AMP. I just don't know the mechanism on the top of my head. So that's how biology does it. They activate it. And so that brings us to the synthetic challenge. So when it comes to making amides in the field of organic chemistry, the goal was we've got to make a protein just as well as nature can. That being said, biotech has made that a neat point. Does anyone know what recombinant protein expression is? You can take a cell, you can insert a gene for the protein you want, and you can hijack the cell and just force it to overexpress the protein you want. Then you lyse the cell and you purify the protein you want out. So that's how people really make proteins. They do it through recombinant protein synthesis, which those who take the advanced biochemistry lab will be doing some of that. But pretty much recombinant protein synthesis is hijacking a cell and making it do your bidding. Biotech is awesome, right? So maybe practically this doesn't make sense in the age of biotechnology. But before biotechnology and recombinant DNA technology existed, the goal was, can we synthetically make a protein? And will the protein be as good as a protein made by a cell? And the answer, ended up being resounding yes. But in order to do it, we had to find a way to make the amide bond directly from a carboxylic acid and an amine. That's what they needed to find, and they needed to find tons of different ways to do it. And we did. And actually the epicenter of the synthetic amide revolution that eventually allowed us to make proteins synthetically, with the chemistry I'm about to show you, was just maybe about 15 miles down the street in La Jolla at the Scripps Research Institute. Does anyone know what the Scripps Research Institute is? It's over in Torrey Pines, it's across the street from UCSD. The Scripps Research Institute is arguably the leading bio/chemical research institute in the world. So graduate students choose to go to Scripps over Harvard. I have known several people who chose Scripps over Harvard because it's Scripps, and Scripps in the field of chemistry and biochemistry, Scripps is a better name than Harvard to get your PhD, arguably. So what I'm trying to say is 15 miles down the road is this little campus. You guys know where Scripps Green Hospital is? Right in the Ocean Lake, Torrey Pines. The leading place to do research, arguably in the world, is right next to Scripps Green Hospital in this little non-script building. But that's one of the best places to do chemical biology and organic chemistry research in the world. Now you know. So this chemistry I'm about to show you was developed there. Or a lot of it was developed there. And I can't stress this enough. Scripps is a really cool place where some of the most important scientific breakthroughs in the last 20 years have occurred, and it's just 15 miles down the street from where we are. And half the faculty at SDSU are from Scripps. So SDSU is very much a pro-Scripps university. I've never been to Scripps. I chose to go back east. Because I'm crazy. So, how do we make amides? And so, the way we developed to make amides from carboxylic acids, thanks to our colleagues down the street, is through what we call carbodiimide synthesis, amide synthesis.
Is that a carbon in the middle?
Yes, that's a carbon. Let me draw the carbon in a different color. So it's an sp carbon with 2 double bonds to a nitrogen. And then we have varying substitutions of the carbodiimide. So this reaction is going to be, this reagent here is called DCC, where the DC stands for dicyclohexyl. Dicyclohexyl. And this C here is carbodiimide. So carbon bound to 2 double bond amine. So those are the mix. So this is carbodiimide. So DCC. And in a carbodiimide reaction, you take your carboxylic acid, you let it stir for a few minutes with your carbodiimide or your DCC, and the reaction, the product will get out, and it's like equilibrium, but there's actually no equilibrium. And you take your amine, so you let this stir, then you add your amine, and you get your amide out. So a couple observations that will help explain the mechanism. Particularly, I'm going to say this right now, the mechanism the book presents makes no bloody sense. I've showed this mechanism to every professor in organic chemistry at SDSU, and they've all agreed with me, what the heck is the book teaching? So don't pay attention to the book's mechanism, pay attention to the mechanism I have in my notes, and the mechanism I'm going to show you right now, which is going to be the same mechanism as in my lecture notes. And the data I'm going to show you right now will explain why the book's mechanism makes no sense whatsoever. And the book's mechanism, I can tell you, I don't know why they taught it that way in the book, because it is not the accepted mechanism in the field. And I feel it doesn't, there are things that if you guys look at the book's mechanism, you'd ask, well, why does it happen that way? And the answer, because why about this or that? And the answer is, you're right, it doesn't happen that way because of what you brought up. So the book's mechanism, I'm sure they have a reason why they did it. The people who wrote the book are very, very, very intelligent people. I'm sure they had a pedagogical reason why they taught it that way. It's just not the accepted mechanism in the field. But the things I want to point out, the little experimental observations. So I said, you let the carboxylic acid and the carbodiimide stir for about 5 minutes. And then you add the amine last. So what happens if you add the carboxylic acid at the same time as the amine? So you add the amine at the same time as the carboxylic acid. The amine is going to deprotonate the carboxylic acid, and you're not getting any reaction. So you have to add the amine last. So if amine is added first, no reaction. There's going to be no reaction. The second thing they found, and this will explain the mechanism, what mechanism I'm proposing is more accepted, is If you add extra base, the reaction is significantly slowed. So extra base equals slow reaction. So what this pretty much means is, for the first step of the mechanism, we need the carboxylic acid. It will not work with the carboxylate. So what these two things show is, first step, first steep, apparently I want T right now. First step needs carboxylic acid. So in other words, the amine or extra base cannot protonate the carboxylic acid for a reaction to go. The proton is needed to react with this. And the book doesn't do it that way. And this data explains why the book's mechanism doesn't make sense. So let me go through this mechanism and compare it to the biological mechanism if I could. What was that? Oh, it wasn't mine. Who would put a marker there? So, the carbonate imide mechanism. MECH, short for mechanism. So as I said, the first thing we do is we take the carboxylic acid, and we take the carbonate imide, or the DCC, and we let it stir for 5 minutes. So we know for this first mechanistic step to occur, we need the carboxylic acid. This will not work with the carboxylate. So what do you think the first step will be with these two reagents? Oh wait, so what's going to deprotonate the carboxylate? One of the nitrogens in the DCC. Absolutely, of course. So here's why we have to add the amine, the coupling partner, the other amine last. These are sp2 amines, right? What's going to be more basic, an sp2 amine or an sp3 amine? An sp3 amine is going to be more basic. So if we add the amine first, we won't be able to do this step of the mechanism because the sp3 amine is going to grab the proton, and we're not going to be able to have our reaction happen. So the first step is one of these amines grabbing the proton. So instead of drawing a 6-membered